Hello, everyone. We will be moving on to topic 9, which is on linear regression. So, from the word linear, you see line. So, we're going to be working with straight lines in linear regression. And this is your typical course design, goals, learning outcomes, assessment, and activity. I'll leave this up online for you to read on Moodle. So I move on to the next slide, which is actually linear regression. So as engineers, we often have lots of data. Sometimes it's just two quantities. So one could plot on the x-axis, the other could plot on the y-axis. And in those cases, we refer to the data as being bivariate. Sometimes you can have more than just two data sets. So those will be multivariate data sets. So for simple linear regression, meaning simple bivariate linear regression, you have only two quantities. And typically they are regarded as the X and Y data sets. We're going to talk more about this and give them more strict definitions. So many times your X and Y data can fit on a simple line. Sometimes the data is so complex it's not linear. So you wouldn't be able to fit the data set through with a straight line. In those cases, we have other models that can fit the data. The process of finding the equation of the straight line that goes through a linear data set is called linear regression. And we're going to go through the process in Python in the class on Friday. Regression describes how an independent, also called exploratory variable, which is your X, is numerically related to the dependent, also called response variable Y. Basically, the variable that changes in response to an independent one is the dependent or response variable, typically referred to as Y. The variable that drives the change in Y is X, and it is independent and also referred to as exploratory variable. So your regression describes the relationship between the dependent and the independent data set. Correlation is a statistical measure of the relationship between X and Y. And in part 2 of this lecture series, so I'm going to record the lecture in 2 parts just to minimize the size, and each one will probably be about 20 minutes long. So the first part, which is what I'm doing right now, will be on linear regression. The second part will be on correlation. So let's move on to the equation for linear regression. And right now, we're just looking at bivariate data, meaning only two variables. The independent variable is X, this guy, and the dependent variable is Y. And I have all of those set up here. So that is your dependent or response variable. It's the variable that responds to a change in the independent or explanatory variable. The other two terms are coefficients. They are called least squares coefficients. And the reason is because the process by which we find those variables is called the process of a least squares fit. So we'll be finding the line that best passes through the data set by minimizing the least square error. So those two terms, A0 and A1, are referred to as least squares coefficients. The first, which is A0, is the intercept on the y-axis, whereas the second term is the slope of the line. And I'm going to show you that graphically in the next slide. And there are some definitions here which I already went through. The variable that is changing is your y, is the variable you're trying to explain, whereas the independent variable is the one driving the change in the response variable. So that's what causes y to change. It's independent, but y is dependent on that. The slope, which is this, explains how much a unit change in x affects the change in y. So that's what the slope does. If the slope is large, then the change in x will result in a large change in y, and vice versa if it is small. So this is an example of a simple bivariate linear regression. The red dots are the data as shown here. So the general trend looks linear, so we are able to fit this straight line through the data set. And this straight line is the line of best fit, which we'll be talking about on the next slide. I have introduced two coefficients, which is A0 and A1. And I said A0 is what? A0 is the intercept, and it's precisely the y-intercept. So how do you find it? You extrapolate your line of best fit, which is the blue line, to the axis. Wherever it hits the y-axis, that is the intercept. So this is about 72, thereabout. So A0 is 72. It's the y-intercept. How about A1? A1 is the slope. And what is the slope? Change in y divided by change in x is your slope. So slope, which is A1, is delta y over delta x, which can also be written as y2 minus y1 divided by x2 minus x1. So we've basically gone through all the parameters in the equation for linear regression. And the equation once again is y equals a0 plus a1 x. This is pretty much the same equation you learned in high school as y equals mx plus b, right? Mx plus b. So b is a0, the intercept, and m is the slope, which is a1. And the reason we use this form is because you're going to see you can actually extend it out to have multiple independent variables, which is what we will be doing in topic 10. So let's move on to the next slide. Oh, before moving on, I have some annotations here. The fact that the line is rising with increase in x, the blue line is rising with increase in x, means the slope is positive. So delta y over delta x is positive. That is a positive association or correlation. I'm going to clean out this so you can see. So that line, the blue line, is the line of best fit, which is also known as the least squares line. Line of best fit or least square fit, same thing, is the blue line. It's what you get when you plot y against x using this model. And lastly, I'm showing that the closer the red dots are to the blue line, the higher is the correlation coefficient. So how do you find the least square fit, which is also known as the line of best fit? How do you find it? I already explained at the beginning that this is called least square fit because we minimize the square of the error. So least squares, minimum of squares error. And the way we do that will be illustrated here. So we pick this point right here. And so I don't write too much, I already annotated it here. We're zooming in on that point, and this is the same point, and this is the model line, and this is the corresponding point on the model. So this is your actual data set, right? Which is the red dot. I talked about that on the previous slide. Y sub I hat is the value you get from the model, meaning when you use this equation of a straight line, you see that this is the equation of a straight line, right? So this is A1, x is the same, right? Plus A0, so intercept is 46, slope is 194. And the residual error is this distance. So yi minus y hat sub I, which is precisely this. That is the residual error. And that is what we need to square, then sum up. And why do you square it? The reason you square it is here, it's positive, right? Because yi is greater than y hat. But sometimes it's negative. Here is negative, here is negative, 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 here positive. So if you just add them up, I mean you add up this without squaring it, the positive ones will cancel out the negative ones. So what we do is to first square it. So you're going to square that error. So the error is y I minus y I hat. So you square it first. So square each of these errors. After squaring each of them, then you sum them all up. So I'm actually going to clean this. This equation is also going to be written out later, but so I going from 1 to n, that's your error. The sum of squares. So this is your sum of square. And the reason we squared it is to account for the fact that the differences could either be positive or negative. And like I said, to find the line of best fit, we minimize the sum of square error, which is why it's the least square error. And this equation right here, it's what is given here. This is what you need to do to find the blue line. Minimize the sum of square error.